You have chapter 12 for me. So, um, the exam's Wednesday afternoon. What questions do you have for me? I would point out the following. Formula sheet from exam 2, exam 3, and a new one. You'll have to turn them all in with the exam, whatever ones you use at the exam. There you go.
For like chapter 11 or 12, just like, because we're not doing a style on it, are we mainly just like, we're gonna just write how to like tell you how to like interpret it?
Right, so like, I will give you the ANOVA output, and I'll ask, what can you tell me about whether the question we're posing is true or false, whether we should accept or reject the hypotheses? You'll have to do what are the hypotheses, right? And then should you accept them, should you reject them? I did post a review sheet with several examples, and I'll post the key to that as soon as class ends. Again, with the regression, here's what I got out of Excel. What's the equation? Here's the graph. What do you think? Here's the actual F test. What can we say about the goodness of fit? What's the R score? It should all be in that data chunk we get out when we do the regression in Excel. So here's that. What does it tell you? Yes.
Since we're not using formulas as much for the interpretation part, what can we put on our little formula sheet to help us with those kind of analysis? That would be a worked out exam.
So we could put down the variable versions of the null hypothesis, right? For means, the null hypothesis is all means are equal. For one factor, for two factor, all of the contributions from A, all the contributions from B. I can write it in the variable terms.
But if F is greater than F, stat, then reject.
Sure, because there's not an example there, is there? That's a rule.
Okay.
Absolutely, you can write down what's my decision rule. I think we used both of these on the variance tests at the very end of chapter 10, where we asked did variance change, which is what ANOVA led us to. That was the result for, I think, the last question on the last exam. So you could write something like that. Absolutely. That's not a worked out example. It's just a rule. Yes.
We know to do it back in cheat sheet again.
Yeah, I can. You came in, I already put it up, but you get a third one. So you use the ones from exam 2 and 3, and now a new one.
And what can we like?
That's, she was saying, if it's not a worked out example, you can write a decision rule. But you should write down things like, for this type of test, I want to make this my null hypothesis. I want to make this my alternate hypothesis. As long as it isn't a particular example, write it in variable terms, right? Let's see. H null, mu equals mu zero, H1, mu not equal, mu zero is a two-tailed test, right? I can write that down exactly like that. I could write, so mu zero. So this is a right tail, this is a left tail. But writing something like that, that's not a worked out example. That's the definition right out of the textbook. I'm perfectly happy with something like that. Felix, make sense?
What percentage of each chapter are you doing?
I broke it out roughly equally. So there's a little less in chapter 11 and 12, but it's about a quarter, maybe 22, 23, 22 or 23 in the last chapter. But I did try and break it out roughly equally. Yes.
So even though so even though we didn't have a cheat sheet for the first exam, we should still expect.
Oh, yes, there'll be questions from the first exam.
I was just gonna ask where getting the tables, stuff like that as well.
You'll get all of the standard tables that we got on the first one. So you'll get the binomial table, the normal distribution table, and the t-table. So it's what, 5 pages of tables.
What's something that you think for this test people would forget to study for?
I think what people forget the most here is the same thing that most of you forgot on exam 3. Study what the hypotheses should be before because before you do any of the math, you need to know what your question you're asking. And then I would go back and, as you said, go back to the first exam. What did data types and depth and census and survey but you've seen all this stuff before. I guarantee you there will not be a question on the exam that is not, at least in some way, something you've seen. Whether it came out of a other exam, out of a homework key, you'll have seen it. I don't pull out of thin air. If I haven't spent a lot of time testing you on it before, it is very unlikely that I will test you on it now. Sure, pick one. So let me pull up our Canvas page. So 7. Are college students more likely than young children to eat cereal? Researchers surveyed both age groups, and the results are in the table below. Okay. So I'm just going to copy down the numbers so I have them, so I can keep scrolling. X1, this is college. X1 is 833 out of N1, which is 860. Young children. X2 is 703 out of N2, which is 750. State the hypotheses used. All right. The fact that I see not an average given tells me I'm probably doing proportions. When I go back and I say, oh, wait a minute, I've got X1 and N1 and X2 and N2, I expect to be doing some sort of test of a proportion. So, a null hypothesis. There's no, right? Null, no. there's no difference. So I could either say there is no difference, but it says are college students more likely. So I'm going to say either they're the same or less as my null, and more will be my alternate. So in terms of proportions, I would say proportion 1 is less than or equal to proportion 2, would be my null hypothesis, and my alternate would be proportion 1 is bigger than proportion 2. I wrote these in pies, right? So I have either pi 1 is less than or equal to pi 2, college students are less than or equal to young children, or they're greater than. And if you do it as subtraction, then you can compare it to the difference to 0. Now, what's my decision rule? At 5%. Okay. Now I need to know what my calculated thingy is. Do I calculate a t or a z when I'm dealing with proportions? I always do a z for proportions. So if I'm doing alpha's 0.05 and a one-tail test, and not just any one tail, a right tail, I want to know if it's bigger than, right? So I'm going to reject when I'm above that 95% number. But this 95% number for z's is one of the numbers I know. It's 1645, not 1.96. Okay, so that's the one. It's 1.96. So I'm going to say my decision rule is I am going to reject the null hypothesis if my calculated value is bigger than 1.96. Oh, and now I realize that 1.96 is the two-tail version. What happened when I was the table's in front of me? Where's my table? Nothing. I ate my table.
It's 1.6.
1.645? Yeah, I looked at the wrong number. 1.96 is the 2.5% number. That's the two-tail 95% number. So I'm using 1.645 instead of 1.96. So if it's bigger than 1.645, again, if I'm bigger than, I'm going to reject. The number in this case is the thing I got wrong. Trying to do it from memory. Bad, Dr. Sassmore. Don't do that. Okay. Now I actually do the calculation. I have my two proportions. P1 over x1 over n1, x2 over n2. And since I'm doing a z, I'm going to do a pooled variance. I'm going to assume that the variation in each one is the same. I'm going to pool these to do the variance. So I do a combined. So 833 plus 703 is 1536. 860 and 750 is 1610. Divide those to get the pooled variance. I think in the notes we used P sub C for combined. Okay. This is kind of small. How can I make this bigger? You, get out of the way. Where's my zoom? There it is, up at the top. 1, 2, 3, 4. Much better. Now I can actually read the damn thing. So there's my combined variance. Now, the Z calculation is the difference between the two over that really nasty looking thing for the variance. I take the proportion, 1 minus the proportion, multiply those together, and then do 1 over each of the number of options and add those. Hey, I get 2.99. That's bigger than 1.645, right? Reject the null hypothesis. What does that mean? Which means that in this case, the college students are more likely to eat cereal than young children.
So there are two different things I want when I ask, what's your answer? I want to know, what did you say or do about the null hypothesis? And then, what does that mean for this setting? Make sense, Haley?
I was gonna move on.
Okay, I'm more on this. I thought I saw another hand. I'm hallucinating. I like that. Okay, so again, I need to know, again, this is, I think, an easier idea than just, hey, do this. Let's walk through each of the pieces. Okay, talk to me.
Last exam, I had a lot of don't use z-test or don't use t-test, use z-test on this. I know now that proportions are always z-test. How can I make sure that I don't make the same mistake going forward?
Okay.
You decide if it's a t-test or a z-test.
When we are testing for means, I need to know one thing. I need to know if I know the population standard deviation variance. So I believe there was a problem back here at the beginning that said, I have a bunch of things and I weigh them and I put them on a scale, right? And the question was, should I do T or Z? Because this is a confidence interval, but it's the same idea. Should I use the T value or the Z value to get this? Does anything up there in the statement of the problem talk about the standard deviation of not just my little group, but the whole process? It says right here, the sample standard deviation. I don't know about the whole candy making deviation. I only know about this group of 10. That's a T, not a Z. If here's my water bottle problem. The key word in here is what? Felix? The whole process, not just the group, the whole process. This water bottle facility is known to vary by up and down 6 milliliters in either direction. Whole process, Z, not T. More questions? Yes. So this is terminology regarding the way a one factor ANOVA is done. So, so here, I've got two factors listed, right? But we only really care about one of them, don't we? What are we actually testing here?
Types of fuel, change the performance, fuel economy performance.
So really, I want to know about the fuel. I don't really care about the vehicle size, do I? So there's an option here to talk about one factor being important and the other one not really being important. So if I am thinking of this as a randomized block, in other words, I only care about this, I don't care about this, that's my definition for a blocking factor. Take a look, page 429. In a randomized block model, the column effects are the treatments. They are the effects of interest, and the row effects are blocks. They're the ones that we just assigned. Well, really, in this case, we pulled vehicle size at random and said, maybe vehicle size is correlated to this, but we don't care about it. So that's our blocking factor. In the example, we're talking about the fertilizers and the soil type. But I don't care what type of soil we use in the example because I know what type of soil is on my farm. I care about what the difference is that the fertilizer causes, right? So I have a treatment factor, something I care about, and a blocking factor, which is literally just there to control for other variables. You're welcome. Yes, sir.
The final exam, is it gonna be like stuff from exam 1 and then exam 2 and then 3 in order?
Yep.
Is it just
Nope, it's in order.
Okay.
Look, I gave it in order. You might as well keep it in order. Yeah, that's always easier.
I usually don't get to every question. What would you suggest for speeding up on these? Techniques. Faster up
Okay,
the test.
no. Techniques for moving faster. I have 3 techniques that I think help me move faster. The first is that I will read most of the questions before I write anything down. I'll flip through the exam, just, oh, okay, this is about this, this is about this, this is about this. And if I see something and I go, what the, I'm going to put a question mark at the top corner of the page so I know when I get to it the first time, skip it and come back to it. So I can get to stuff I know that's beyond there rather than get hung up on that one page. Secondly, the more recent stuff, because as I just told Tony, it's in order, the more recent stuff's at the back. If that's fresher, start there, work backwards. When it comes to actually going through and solving every problem, if it takes you more than a minute or two to go, what the hell am I supposed to be doing here? Stop and move on. And come back. But that's going to make a dramatic assumption that you can at least get through the first pass and get time to come back. If you keep going, I don't know what I'm doing, I don't know what then take a deep breath, close your eyes for a moment, stand up, shake it off, and then sit back down and do it. I had a disastrously long master's exam, one of my candidacy exams, where you sit down and it's just you and a sheet of paper for 3 hours, let's go. I wish I was making this up. It was 9 questions. That was it. I was there for 3 solid hours. And I stood up every half hour, walked around the table in a little circle, shook my whole body, sat back down and started again. If it works for you, it works for you. Maybe it doesn't. I don't know. That's you. But I find I start to get tense, physically tense, when I start to feel like I'm stuck in something. If I can relax my body, I can relax my head. I hope those help.
But like, you haven't tested it all at once, full again, so would you suggest like going through like your review guides, all of them again? Would you rather we do that than like spend countless hours just looking through pages?
I think you're better off looking through the exam keys and the exam reviews and things like that. The homework keys, things I've asked you about already are likely to come back up. Things that I have never asked you about, if this is the first time I'm asking about them, unless it's in chapters 11 and 12, that's a 2x4 to my head. And I will have earned it. Yes. More questions, ask me more stuff.
If you only had 2 days to study for it, where would you start? Would you start on the homework or would you start on the exam?
I'd start on the exams. And then I'd go to the homeworks. But I'd probably go back and forth a couple of times. It also depends on what else I'm doing the next 2 days, right? Because I'm not the only class you have. I might be the only exam you have, but I'm not the only class you have. You never know. I will say the following. It is a good thing our exam is late in the afternoon. So that means you should get a good night's sleep. I hope. At the very least, take a nap before these. If you come in hyped up on caffeine and your hand looks like you're writing a seismograph instead of words, I won't be able to read it. That's a bad thing. You don't want to be so hyped up on caffeine that you can't sit still during the exam. Eat a reasonable meal far enough in advance that you're not going to be sick in the middle of the meal, either passing out from hunger or letting your lunch revisit us. We have time. I have office hours here and here. You can keep asking me stuff up until the last minute. But I think you should get it in before then. So what else do you have for me?
What are some of the silly errors you've seen people do on the final
Oh my.
for this class specifically?
I saw people miss a page. Like 2 pages stuck together and they turned them together and the whole page was blank. And it was in the middle of the exam, not close to the end. So I'm like, well, there's nothing written on this page. So please make sure you look at every page. The other most common errors I see made are people who use the wrong distribution. So T instead of Z instead of T, or normal instead of uniform, discrete instead of continuous, or vice versa. So we had all these different options. Please make sure you read the question carefully because it will tell you which one I want you to use. And then you can get that out. What else have I seen a lot of? I don't know that word. That was really my big set. Yes. 19. All of them have multiple parts. So I said 2 or 3. So it's a bunch of little questions like the other exam was, right? A, 2 points. B, 2 points, sort of deal.
Exam valued higher than the last exam, or is it the same?
It is valued higher, but just barely. Because it is a comprehensive exam, it should weigh just a little more. Syllabus. 4% more? Wrote it in the syllabus. Where is my syllabus? Here it is. There we go. 4% more. I knew I had that information somewhere. An exam is not designed for me to F you over as hard as possible. An exam is designed for you to show me that you've gotten material from this course into your heads and can thus explain stuff back to me. My hope, my goal is for this exam to show me that you learned something this semester. Not, oh, I got you with this one. No, that's not. Yes.
Could you just like touch, I don't know, that's not like super specific, but just like touch base a little bit more on like the PDFs and the CDFs and, just like any, maybe mistakes that you see, you know, with the.
Okay. Um,
I guess so.
no, but remember that a PDF is designed to give me a single value. So when I think about a probability distribution function in the discrete case, I'm thinking that I'm going to get the probability for a particular value. So what is the chance I did this thing 5 times and I got 2? Or what's the chance I did this experiment and I got a 7? I'm looking for one value. If I'm looking for a cumulative distribution function, I'm looking up to that number. But it's always less than or equal to. Which means if I ask for something about more, you need to do it the other way, right? 1 minus. And I keep drawing pictures for all of these with the shading like we do in the continuous case, so that I can remind myself which way I'm supposed to go. All of the formulas are in the textbook. You get formula sheets, put them down. For the uniform one, for the binomial one, for the normal, and for the uniform continuous. We get all of those. Write them down, that way you have them, you don't have to try and regurgitate them. Better?
I know on the previous sheets, we're not really allowed to like add stuff to it, but if we were something that just messed with stuff last week, and we cross it.
Oh, yes, yes. Don't re-edit them substantially, but if you want to take that off, put something on the new sheet that fits it in better, that's fine. I don't want it to look like a redacted version of the STAR report. It's an Epstein file. I got 18 more minutes with your name on it. Ask me anything you want, but I don't have a reason to keep you nailed to the chairs.
The p-value for the interaction effect just between 0 and 1.
A p-value is always between 0 and 1 because it's always a probability, right? Whether it's a p-value for the interaction effect or anything else, a p-value should always be between 0 and 1. Sometimes they're written in that weird scientific notation, right? 1.8 times 10 to the negative 4th, or e negative 12 or something like that. It's still between 0 and 1.
If you want us to interpret the p-value,
Mm-hmm.
is it enough to just say we reject the p-value or whatever, or we reject the null hypothesis? Would that be an interpretation, or would you need like something?
Well, I suppose it depends on if we only have one p-value, then really I'm asking, is it close or is it far? So for example, let's say my alpha was 0.05, like it was in the previous example. And you gave me a p-value of 0.477. You're going to reject the null hypothesis, sorry, 0.0477. You're going to reject the null hypothesis. But it's fairly close, isn't it? If you give me 0.0002, that's a really strong interval. Okay, so there's lots of evidence. So I suppose it depends on if there's more than one, is one value strong, is one value weak? Does one matter more than the other? Is the interaction effect really, really big? Or is the interaction effect basically negligible? There are lots of different interprets for the p-value, but it could simply be, we rejected the null hypothesis, we're done.
Are we gonna have to draw any charts?
Draw
Graphs?
charts. I did almost all of our graph making in Excel. You're welcome to draw pictures that you think help you, but am I going to force you to draw? No, this is not an art class. I got in enough trouble trying to draw a normal distribution that didn't look like an F distribution.
Which one do you use, like, you explain?
Yes. There are really three different places we use a t calculation. We either are using it for a hypothesis test. That's chapters 9 and 10, right? And again, it's assuming I don't know the overall standard deviation. I only know my sample standard deviation. Well, then my t calculation itself comes from this calculation. The t average for a mean, the x bar from my sample versus my benchmark divided by my standard error. So that's for a mean, right? If I am doing two sample, then we've got two questions. For a two sample test, the question is whether or not we get to pool the variance. And then there are two different t's. The top one assumes we've pooled the variance. The bottom one assumes we didn't. In the top one, we have big, ugly calculation for the pooled variance. In the bottom one, we have big, ugly calculation for degrees of freedom. But those are two sample. That's why there's x1 bar minus x2 bar. The only other place I typically use a t-value isn't actually for a test. It's for a confidence interval. But I say, oh, I'm looking for a mean and a confidence interval, and I am trying to figure out how big my confidence interval should be. And again, the only difference between the Z1 and the T1 is whether or not I know the population standard deviation. But that's the same number we were using, right? T alpha then S over N. This is the same thing from our t-test, wasn't it? Only we're just using it now as the margin of error on either side of the average we were given. So really, there are three places I can rule in a t-value. There were a bunch of other t calculations I could do for things in regression, but I'm not doing those tests by hand. They're just going to pop up in the information, so I have to generate those numbers. Yes.
Right in the conclusion, that are not graphs as a diagram,
Okay.
but that like norm formulation in terms of norm by little bigger or equal to 20, you can still do the same but with the t calculation.
Yes.
This one.
Yes.
What happens if it's smaller than 30? What?
This is something we didn't cover in this particular course, but there's a method where I can actually say, I don't have enough information So let me resample that information multiple times with replacements. So I take a number, I throw it back in the pile, and I randomly pick numbers over and over from my own pile of data. That's called bootstrap estimation. And it's a way of enlarging your data set, but it also compounds your error possibility. So there are all sorts of pieces called bootstrapping methods. We'll talk about next semester in the decision analytics course, Fit 451. BU 451, the course that comes after this one, where we talk about increased methodologies for bootstrapping, among other things. But yes, if we don't have 30, I should be using a different method altogether. So that's why all of our populations have been large. The other thing I do is that finite population control factor thing.
Yeah.
And I could adjust my t-value that way. I don't like those. They're really hedging my bets. But in really small populations with really small samples, I'll just use a t and hope for the best. That's part of why, even though in that very first example we did today with the candies, I didn't have more than 30, but I still said I want a t-value for a confidence interval there, because I don't have any of these methods without a computer in front of me. One of the problems in statistics in general, beyond this course, applies to every course. Data that is accurate and complete is hard to come by. So a lot of what we do is figure out where the data itself might fall short and how do we adjust for that. One of the biggest pieces of data gathered in this country is all of the economic data for things like the consumer price index and therefore the rate of inflation. Things that the president and Congress have all been talking about for the past, oh, I don't know, 30, 40, 50 years. But the consumer price index states up front that fuel and housing are too volatile to make good benchmarks. So gas prices, while they go up and down seasonally, should not be counted when we do the consumer price index. They're considered a too volatile a piece. They get pulled out. So we've taken the data right away and we've gone, okay, chop that off. It's got too much fluctuation to give me anything, too much noise for the signal. Then you look at food prices. Well, food prices are a wonderful thing to judge, right? How much does a cup of coffee cost? Where are you buying it? If I go to a Starbucks in Pittsburgh, I will pay more than if I go to Starbucks in Greensburg. I will pay more than if I go to a Starbucks in Athens, Georgia, or Morgantown, West Virginia. So regional price changes versus national price changes. So you have to then take the region and say, well, there's a lot of people here, that part should matter more. There's very few people here, we want to count that a little less. And those sorts of additional estimation behaviors to smooth my data, to make it more useful, is a lot of what statisticians argue over. That's the downside to a course. I made all of these rules and they work when you have good, complete data, something that is rare. More questions? This means I will see you all on Wednesday. Our exam starts at 3:30 in here. I will be in the Enrichment Center before that. I'll be in the Enrichment Center tomorrow morning. If you've got questions, come bug me. Otherwise, I'll see you all then. Good luck on the rest of your finals as well.